How much does a single choice echo across the cold embrace of the void? Humanity reaches for the moon, yet our grandest ambitions are often tethered, not by the limits of physics, but by the inertia of old paradigms. Is the struggle against the cosmic tax of mass and trajectory, or against something far older, far more ingrained within our own methods? The current baseline for lunar exploration, the Artemis Plan, casts a heavy, and almost gravitational, shadow across our path. It begins with the expendable, billion-dollar SLS Block 1, the foundation for Orion's journey. Orion itself, with a limited 1,300 meters per second delta V, struggles to propel itself from low Earth orbit, requiring a larger 3,100 meters per second for its trans-lunar injection. It cannot independently descend or ascend from lunar orbit. Furthermore, its mandated reliance on the distant near rectilinear halo orbit compounds this burden, demanding an additional 1.5 km per second delta versus for round-trip lunar surface operations. This forces the Starship human landing system to carry approximately 45 additional tons of propellant, swelling the overall demand to an astonishing 400 to 450 additional tons of fuel on Starship before departure. This is not mere inefficiency, it is a cosmic drain, a forfeiture of precious resources to an outdated design. But a different path exists, a whisper of a simpler, bolder trajectory. The proposed Orion on the nose architecture replaces the cumbersome near rectilinear halo orbit with a streamlined low lunar orbit rendezvous. This radical shift reduces the fuel required for descent and ascent from 5.5 km per second to 4.0 km per second, saving a crucial 1,500 meter per second delta versus for lunar surface operations. The ripple effect is profound: 450 tons of fuel saved, the equivalent of 5 tanker launches. This slashes mission cost, time, and risk. This faster, simpler trajectory also significantly reduces propellant boil-off by minimizing cryogenic fuel storage time in space, and shifts critical mission phases closer to Earth, offering wider, more forgiving launch windows for Orion. Moreover, Starship transforms from a mere lander into the main deep space habitat, offering astronauts approximately 600 cubic meters of habitable space compared to Orion's compact interior, a profound shift from a cramped capsule to a true cosmic haven. This tension between the revolutionary and the established echoes even closer to home, in the very methods we use to return from the heavens. Elon Musk and much of the aerospace industry have long viewed ocean splashdowns as an outdated, inefficient relic. They necessitate complex, weather-dependent logistics, expensive ships, helicopters, medical teams, and the insidious corrosion of salt water that increases refurbishment costs and slows turnaround. SpaceX's Dragon, a workhorse with over 50 successful cargo and crew missions, and rapid 137-day return to flight for capsules, proved its propulsive landing concept possible with a 2016 hover test in McGregor, Texas. Its 8 Super Draco engines, each capable of 16,000 pounds of thrust, were designed for this very purpose. Yet, the revolutionary path was cancelled in 2017. The reason? NASA's preference for parachute systems, a technology with a long flight history since the 1960s, prioritizing schedule certainty and domestic crew launch capability restoration over risky revolutionary methods. The decision was driven by the comparatively lengthy certification process for a system never operationally proven for crewed spacecraft. We stand at a precipice. The immense efficiency and expanded capability offered by Starship's architecture for deep space, and Dragon's unfulfilled propulsive landing potential, beckon us. Sierra Space's Dream Chaser, designed for runway landings with less than 2 gigaseconds impact, aims to replace splashdowns, yet lacks orbital flight history as of 2026. It relies on unproven atmospheric glide tests and a narrow landing envelope. The gravitational pull of established safety cultures and legacy systems continues to define our reach into the infinite. If our journey to the stars is defined by our reluctance to embrace radical efficiency, what other grand ambitions might be silently curtailed across the cosmos?